Most people like the first half of the story. They like hearing that the atoms in your body were forged in stars because it sounds grand and beautiful and safely distant. The kind of sentence that belongs in a planetarium voiceover while a galaxy turns slowly above your head. And it is true. The calcium in your bones, the iron in your blood, the carbon threaded through your cells were not manufactured on Earth. Those elements were built under pressures and temperatures so extreme that ordinary language almost fails to describe them. Inside stars that lived collapsed and scattered their contents long before this planet had oceans, trees, or anything with a face. That much people are happy to accept. The uncomfortable part begins one step later when you ask a very plain physical question. If your body is built from ancient matter, what exactly happens to that matter when the body is burned? That is where sentiment stops being enough, because now we are not talking about metaphor. Memory, or ceremony, we are talking about thermodynamics. The first law tells you something blunt and unromantic. Matter is not erased because you find the event emotionally overwhelming. Energy is not suspended because the moment feels final. In every ordinary physical process, substance is conserved, it changes form, changes location, changes the way it is bonded. But it does not vanish simply because the pattern it once belonged to has come apart. Cremation feels absolute from the human point of view because what we recognize as a person no longer remains intact. Yet physics does not track persons in that sense. Physics tracks mass, energy, temperature, pressure, chemical bonds, and motion. By that accounting, cremation is not disappearance. It is conversion. I have always found that distinction strangely clarifying. A human body looks stable because your eyes are not built to see exchange rates at the atomic scale. You see skin, bone, expression, posture. You do not see oxygen moving in and out of tissues, carbon entering through food, water leaving through breath, salts shifting across membranes, proteins assembling and breaking down. Even while you are alive, the material that composes you is in traffic. The body maintains a recognizable form only by constantly replacing its own ingredients, which means the thing you call you is already less like a statue and more like a sustained process. Once that process stops, heat can do in hours what time and bacteria would otherwise do much more slowly. Break organization apart. Inside a cremation chamber, that breakdown is dramatic only at the scale. We notice at the scale that matters to chemistry, it is a sequence of familiar events. Water evaporates. Soft tissues dry and decompose. Organic molecules lose their structure and react with oxygen. Gases are produced and carried away. Mineral material resists longer. None of this requires a special exception in the laws of nature. And that, to me, is one of the most remarkable things about it. A body capable of love, fear, memory, embarrassment, curiosity, music, grief, and jokes is still made of matter that obeys the same rules as steam, ash, and air. The difference is not that one escapes physics and the other does not. The difference is arrangement. That point can sound cold if you say it carelessly, but I do not think it is cold at all. In fact, I think it restores a kind of honesty. We spend so much of life treating the body as if it were a fixed possession, something sealed off from the rest of the world, when it is actually open to exchange every second. You borrow atoms, organize them temporarily, and eventually release them. The process begins before you are born and continues after the structure has failed. A flame gives you a useful picture here. It has shape, motion, and identity. Yet none of those depend on keeping the same particles in place. Fuel enters, heat transforms, gases leave. And still you call it one flame. A body is more intricate than that. Of course, but not exempt from the same logic. So when we begin this story with star stuff, I do not want it to remain a decorative line. I want it treated as a material fact with consequences. If the atoms in your body came from older structures, then they will also move on from this one. Cremation does not cancel that history, and it does not interrupt it. It simply makes the transfer visible in a compressed and irreversible way. What ends there is not matter itself, but a very specific arrangement that, for a limited span of time, could look out at the world and call it experience if you strip away the language of anatomy, organs, tissues, systems, and push your description down to something more fundamental. The human body stops looking like a biological object and starts looking like a numerical one. You are, quite literally, a count of atoms arranged in a way that maintains itself for a while. Roughly 7 octillion atoms, 7 followed by 27 zeros, held in place by electromagnetic forces, thermal motion, and chemical bonds that constantly form and break without asking your permission. That number is so large that it becomes difficult to feel, but what matters is not the magnitude alone. What matters is that those atoms are not glued together permanently. They are in motion, vibrating, exchanging, drifting in and out of what you call yourself even while you are sitting still. The composition of those atoms is surprisingly ordinary. About 65% of your mass is oxygen, not as the gas you breathe, but bound inside water molecules and organic compounds. This means that most of your body is, in a very literal sense, structured fluid. Around 18% is carbon, which acts as a kind of structural backbone, forming chains and rings that support proteins, membranes, gna, and countless other molecules. Hydrogen contributes roughly 10%, often paired with oxygen and water, but also threaded through fats and proteins, influencing how flexible or rigid those structures become. Nitrogen, about 3%, sits inside amino acids and nucleotides, quietly participating in the chemistry that allows cells to build and rebuild themselves. Then come smaller fractions: calcium in bones and teeth, phosphorus in energy molecules and skeletal material, and traces of elements like sulfur, sodium, potassium, magnesium, chlorine, and iron, each present in tiny quantities but essential for electrical balance, oxygen transport, and cellular reactions. What is striking is that none of these elements are rare. There is nothing exotic in you. The same carbon appears in graphite and leaves. The same oxygen exists in seawater and air. The same calcium forms limestone cliffs. The difference is arrangement. Rearranged one way, these atoms become muscle fibers capable of contraction. Rearranged another, they become neurons capable of transmitting signals. Rearranged again, they become bone rigid enough to support the rest. The atoms themselves do not carry instructions for identity. They simply obey local interactions, bonding when conditions favor it, separating when energy disrupts them. The sense that this collection belongs to you comes from the persistence of pattern, not from any special ownership of material. Even that pattern is not as fixed as it appears. The atoms in your body are constantly being replaced. The water you drink becomes part of your bloodstream within minutes and leaves again through respiration and sweat. The carbon in your food is incorporated into cells and later released as carbon dioxide. Proteins are built, broken down, and rebuilt with new components. Over time, Much of the material that once composed you is exchanged for new material, yet the continuity of structure gives the impression of permanence. It is similar to watching a whirlpool in a river. The shape remains recognizable, even though the water forming it is never the same from one moment to the next. Your body behaves like that, maintaining organization while its ingredients circulate. This constant exchange also blurs the boundary between you and the environment. The oxygen entering your lungs was part of the atmosphere moments ago. The hydrogen in your cells may have been in rainwater days earlier. The iron in your blood might once have rested in soil before passing through plants and animals. At the atomic level, there is no strict separation. There is only a flow through a temporary structure that maintains itself by borrowing material and returning it. Stability emerges from motion, not from stillness. The body is less like a container and more like a crossroads where atoms pass, interact, and move on. Looking at yourself this way changes the emphasis. Instead of seeing a fixed object made from particular substances, you begin to see a dynamic arrangement sustained by continuous turnover. 7 octillion atoms, mostly oxygen, carbon, hydrogen, and nitrogen, held together for a time by chemical relationships that are constantly being renegotiated. The remarkable part is not the ingredients, but the coordination. A shifting collection of common elements forming a structure that remains coherent long enough to observe its own composition. Once heat becomes the dominant force acting on the body, biology loses control and chemistry takes over. A cremation chamber operates in a temperature range roughly between 760 and 980 degrees Celsius, which sounds extreme. But from a chemical standpoint, it is simply enough energy to destabilize molecular organization. Nothing supernatural happens there. No sudden vanishing of matter. No instant reduction to nothingness. Instead, thermal motion increases. Molecules vibrate more violently. Weak bonds fail first. And structure begins to loosen in a sequence that follows ordinary physical rules. If you could watch it at the atomic scale, you would not see destruction in the dramatic sense. You would see motion intensifying until organization can no longer hold. Water responds before anything else because it is both abundant and comparatively easy to separate from the structures that contain it. Cells depend on water for volume and mechanical stability. So as temperature rises, liquid water absorbs energy and transitions into vapor. Steam forms within tissues. Pressure builds locally. And the delicate balance that keeps cellular membranes intact begins to fail. Proteins suspended in fluid lose their environment. Membranes collapse. And the cohesive texture of tissue starts to disappear. This is not yet combustion, just dehydration on a massive scale. But the consequences propagate quickly because so much of biological structure depends on water maintaining shape and spacing. As dehydration continues, proteins begin to denature. Their function relies on folded configurations held together by weak interactions, hydrogen bonds, electrostatic attractions, and subtle geometric constraints, and these are easily disrupted by heat. Once unfolded, they no longer act as enzymes, no longer stabilize cellular scaffolding, and no longer contribute to organized metabolism. Lipids in membranes soften and fragment, allowing compartments that once separated chemical processes to merge. The body, which depended on compartmentalization, becomes chemically continuous. At this stage, what had been a coordinated system turns into exposed organic material, still composed of carbon, hydrogen, oxygen, and nitrogen, but no longer arranged in a way that supports life. With oxygen present and temperature high, combustion chemistry begins to dominate. Carbon-based molecules break into smaller fragments. Hydrogen atoms recombine with oxygen to form water vapor, and carbon atoms oxidize to carbon dioxide. Nitrogen-containing compounds decompose, releasing nitrogen gas and other small molecules. These reactions are familiar. They occur when wood burns or when food chars in a pan. The difference is only in the complexity of what is being broken down. Heat supplies energy, Boltzvika, and atoms reorganize into simpler, more stable forms. Gases expand and move upward with airflow, carrying away the products of decomposition. Throughout this process, nothing happens all at once. It is gradual, layered. Water leaves first, then soft tissues collapse, then organic molecules fragment, then gases disperse. The structure that once maintained temperature, repaired damage, and regulated chemistry no longer exists. So the system follows the easiest thermodynamic path. Increasing disorder, entropy rises because organized molecular arrangements are replaced by freely moving particles. The body's architecture, which required constant energy to maintain while alive, relaxes once that maintenance stops. Heat accelerates the transition, compressing what would otherwise take much longer into a short span of time. By the later stages, most of the material that once defined shape has transitioned into gases and small molecular residues. These move with convection currents, mixing with surrounding air, leaving behind only components whose bonds resist breakdown at those temperatures. The transformation is not sudden but cumulative, a progression from hydrated structure to dry residue, from complex molecules to simpler ones, from confined organization to dispersed motion. Seen closely, it resembles a release rather than a collapse, as if the constraints holding atoms in a specific arrangement have been lifted and the material is free to follow the same chemical tendencies it always had. After water has largely evaporated and the fragile architecture of soft tissue has collapsed, what remains is mostly carbon-based material exposed to heat and oxygen. And this is where the transformation becomes less about structure and more about circulation. Organic molecules, proteins, fats, carbohydrates, DNA are all built on chains of carbon atoms, with hydrogen, oxygen, and nitrogen attached in arrangements that allow life to function. Once those arrangements break apart, the carbon no longer participates in biology. It participates in combustion. Oxygen from the surrounding air combines with carbon atoms, forming carbon dioxide, and the gas does not linger. It expands, rises with convection, and exits into the atmosphere, carrying with it a large fraction of what once composed muscle, skin, and organs. This step is often imagined as reduction, but physically it is redistribution. Carbon does not disappear. It changes partners. The same atoms that were locked into complex molecules inside cells now bind with oxygen in a simpler configuration that is more stable at high temperature. Carbon dioxide is a small, mobile molecule, and once formed, it diffuses rapidly. Within minutes, it is mixed into hot air. Within hours, it disperses into the surrounding environment. From there, it becomes part of the global carbon cycle, indistinguishable from carbon dioxide released by soil, oceans, forests, or combustion elsewhere. Plants absorb it during photosynthesis, incorporating carbon into new organic structures. Animals eat those plants. Respiration releases some of it again. The path is not predetermined, but the circulation is unavoidable. Nitrogen follows a similar but quieter route. Much of the nitrogen in your body resides in proteins and nucleic acids, where it plays a role in maintaining molecular identity. Under heat, These compounds break apart, and nitrogen atoms recombine to form nitrogen gas, a molecule that is already the dominant component of Earth's atmosphere. Unlike carbon dioxide, nitrogen gas is relatively inert, so once released, it simply blends into the vast reservoir above the surface. Over time, bacteria in soil fix atmospheric nitrogen into usable form. Plants absorb it. And the cycle continues. The nitrogen that once contributed to amino acids or genetic material becomes part of a broader environmental exchange, entering new biological pathways long after the original structure has dissolved. What is striking here is how quickly the transition occurs. Material that was confined within a defined shape becomes part of planetary scale circulation. Carbon atoms that were once part of cellular membranes can, in principle, be absorbed by a leaf. Nitrogen atoms from proteins may eventually enter soil chemistry. Hydrogen and oxygen released earlier rejoin the water cycle. The body does not remain localized. It disperses into systems that operate continuously, independent of individual lives. From a chemical standpoint, there is no boundary marking where one organism ends and the environment begins. Only a change in how tightly atoms are grouped. It helps to picture this not as a dramatic scattering, but as entry into processes already in motion. The atmosphere is constantly mixing. Plants are constantly fixing carbon. Microbes are constantly cycling nitrogen. When gases produced by cremation join these flows, they do not create new pathways. They merge into existing ones. Over time, those atoms travel, combine, separate, and recombine in different contexts. The scale shifts from a single organized body to diffuse participation in global chemistry. Nothing announces the transition. It occurs simply because the molecules formed are stable and mobile, and the environment is always ready to absorb them. Seen this way, the release of carbon and nitrogen is less an endpoint than a change in bookkeeping. What was once counted as part of a body becomes part of atmospheric composition, then part of biological uptake, then part of other materials. The atoms continue under the same rules that governed them before, only now they move through larger cycles instead of a single structure. By the time most of the soft tissue has transitioned into gases, what remains is not the familiar structure of a body, but a framework built from materials that respond differently to heat. Bones are not simply hardened flesh. They are composites, part organic and part mineral. And once the organic portion has burned away, the mineral lattice becomes dominant. This lattice is primarily calcium phosphate arranged in a crystalline structure, interspersed with small amounts of magnesium, sodium, and other trace elements. Unlike proteins or lipids, which rely on comparatively fragile, covalent arrangements that destabilize under moderate heat, these mineral structures are held together by ionic interactions in a rigid network that requires far more energy to disrupt. The result is that while most of the body disperses into gases, the skeletal material persists as solid residue. The difference is not about importance, but about bond strength. Organic molecules, even large and complex ones, depend on specific configurations that heat easily disturbs. Calcium phosphate, on the other hand, forms a repeating lattice where ions occupy stable positions within a structured matrix. To break that arrangement, you would need temperatures far beyond those used in cremation. Temperatures closer to those encountered in metallurgical furnaces or geological processes deep within the earth. In the chamber, heat removes water, burns away collagen, and eliminates the organic scaffolding of bone. But the mineral component resists. What remains is brittle, chalk-like material that no longer has the flexibility or resilience of living bone. yet still contains the same atoms that once contributed to structure and movement. This residue is often described as ash, but chemically it is closer to fragmented mineral. The original bone has lost its organic binding, leaving porous, fragile pieces that are later processed into a fine powder. The mass is small compared to the original body, typically a few kilograms, because most of the body's mass was water and organic compounds that have already dispersed. What stays behind represents the densest portion, the part built from elements less inclined to enter gaseous cycles under those conditions. Calcium and phosphorus dominate, accompanied by trace minerals that once participated in metabolism but now exist in a more inert form. It is interesting to consider how different this behavior is from the rest of the body. Carbon, hydrogène, and nitrogen move quickly into atmospheric circulation, forming mobile molecules. Calcium and phosphorus remain localized, at least temporarily, because their preferred configuration under these temperatures is solid. They do not oxidize into gases easily, nor do they evaporate. Instead, they sit in place as the surrounding material disappears. The contrast illustrates how the fate of each element depends less on its biological role and more on its chemistry. The body contains both volatile and refractory components, and heat separates them according to their physical tendencies. Even so, the persistence of mineral ash does not imply permanence. Over time, these solids can dissolve, weather, or disperse depending on what happens next. Calcium phosphate can interact with moisture, soil chemistry, or mechanical processes, gradually returning to broader environmental cycles. The time scale is longer than for gases, but the direction is the same. Atoms leaving a concentrated arrangement and entering wider circulation. The apparent solidity is only a delay, not an exemption from change. What remains in this stage is therefore not a preserved structure, but a concentration of elements that resisted immediate transformation. The atoms are the same ones that once contributed to bone strength and metabolic balance, yet their context has shifted. They no longer function as part of a living framework. They exist as mineral fragments shaped by heat and subsequent handling. The distinction highlights how physical properties govern outcomes. Some atoms move quickly, some remain longer, but all follow the constraints of bonding, temperature, and environment, rather than any biological meaning they once held. At this point, nearly every part of the transformation has been described in terms of atoms changing partners, molecules breaking apart, and material entering wider cycles. But there is still a conceptual shift left to make, because what disappears in this process is not matter, but organization. A living body is not simply a collection of elements. It is a highly ordered arrangement maintained by constant energy flow. Cells repair themselves. Gradients are preserved. Proteins fold into precise shapes. And signals move through structured pathways. All of this represents low entropy, a state in which atoms occupy very specific positions relative to one another. The moment maintenance stops, that organization begins to relax. Bonds break, gradients flatten, compartments merge, and the system drifts toward configurations that require less coordination. Cremation accelerates this relaxation, but the direction is the same as natural decay. The pattern dissolves, while the components remain. It helps to separate two ideas that are often blurred together. One is the persistence of atoms, which physics guarantees under ordinary conditions. The other is the persistence of arrangement, which physics does not guarantee at all. The same atoms can form a functioning brain or drift as independent molecules in air and dust. Nothing in the laws of nature privileges one configuration over another, once energy is no longer applied to maintain it. The distinction becomes clearer if you imagine written text. The ink molecules can survive even if the page burns, but the meaning encoded by their arrangement disappears because the pattern is no longer intact. In a similar way, a body can be reduced to gases and mineral fragments without losing a single atom. Yet the specific configuration that supported thought and memory no longer exists. Entropy provides the framework for understanding this shift. A living organism holds atoms in improbable arrangements that require continuous input of energy to sustain heat, chemical reactions, and time all favor more dispersed configurations. When the organized structure is exposed to high temperature, the transition toward disorder occurs quickly. Complex molecules break into simpler ones. Confined material spreads, and localized concentrations disperse. None of this contradicts conservation laws. In fact, it follows directly from them. Energy introduced into the system increases molecular motion, and increased motion makes ordered arrangements harder to maintain. The result is not destruction, but redistribution, a movement from tightly organized structure to broadly distributed matter. This perspective changes how continuity is interpreted. The atoms that once formed tissues continue to exist, circulating through air, soil, and water, entering new reactions and new structures. Over long time scales, they may become part of plants, animals, or mineral formations. The material does not end, but the pattern that defined one individual does not persist through those changes. Physics allows continuity of substance, but not continuity of form without ongoing maintenance. The only sense in which anything endures is through the continued existence of its components, not through the preservation of their arrangement. There is something restrained but precise in that conclusion. It does not rely on metaphor, and it does not claim more than the laws of nature support. A living body represents a temporary configuration assembled from common elements, maintained for a time by metabolism and repair. When that maintenance ceases, the configuration relaxes, entropy increases, and the atoms rejoin broader cycles. Nothing is lost in the accounting of matter. Yet the organization that once coordinated those atoms no longer exists. The continuity that remains is purely material. Atoms persist, bonds reform elsewhere, and the environment absorbs what was once concentrated